In this video, we will talk about what are combinations in the context of counting problems. So in the last video, we talked about permutations. Now we're ready to talk about combinations. So I want to motivate this with an example, which says, I have 11 books and want to donate 3 of them. And how many ways can I select the 3 to donate? So I first want to notice that it might be tempting to say that, there's 11 choices for the first book that I pick. That leaves 10 choices for the second book I pick, and then 9 choices for the third book remaining. But it turns out it's not just those 3 values multiplied together. So why is that? Well, for example, let's suppose that the 3 books I pick are the second one, which I'll call B2, and then the 10th book B10, and the 5th book B5. So if I were to pick these 3 books, well, that should be the same as if I had picked B5 first, and then B2 second, and then B10 third. Like, it's the same set of 3 either way. So in other words, the order in which I'm picking the 3 books shouldn't matter here. However, this quantity 11 times 10 times 9, it's counting these 2 orders as different. Because 11 times 10 times 9 is saying that, I'm sort of implicitly saying there's 11 choices for the first thing, and then that leaves 10 choices for the second thing. So it's sort of implicitly saying what's first and what's second and what's third matters. So the issue that we're seeing here is, for this problem, the order in which we pick doesn't matter. The order in which we pick doesn't matter. So as a result, this 11 times 10 times 9 overcounts. It overcounts what the actual answer should be. So I'm going to put a little sad face here. So unfortunately, that's not quite right. But we can fix this pretty quickly. So how do I fix it? I want to notice that, if I were to have picked these 3 books, I want to think about, well, how many different orders are there? And let's just consider those orders. So let's think about how many different ways there are to rearrange these. So these can be permuted. That's just a word that means rearrange. These can be permuted in 3 factorial ways, right? Because there's 3 factorial ways to rearrange 3 objects. So 3 factorial 6. 3 factorial ways to rearrange these. 3 choices for what could go first, and then 2 choices for what could go second, 1 choice for what can go third. Okay, so the issue with 11 times 10 times 9 is it considers these 2 orders and all the different ways of permuting them as being different. It's counting them as different when they're actually all the same. So it's counting each set of 3 books 3 factorial, which is 6 times. We are overcounting by a factor of 6. So to fix this, we should divide by 3 factorial. That'll fix the overcounting for us. So if I do that, I'll get 11 times 10 times 9. And now I divide by 3 factorial. That's how much I overcounted by. So if I do that, if I work this out, it turns out we get 165. And that's my answer. So I could write this in a slightly different way, this expression here. And that's going to show up in my formula a little bit later. So let's just briefly talk about how I can write this in a slightly different way. So we saw this in the last video as well, but on the numerator, if I just had some more terms, like 8 times 7 times 6 all the way down to 1, we'd have a factorial. So let's try to get a factorial up top. So right now I have 11 times 10 times 9 up top. And on the bottom, I have 3 factorial. So to complete the factorial in the numerator, we would still need 8 factorial. Okay, and then on the bottom, if I multiply that on the top, I got to multiply that on the bottom. So now if I do that, what I get is I get 11 factorial up top. And on the bottom, I got 3 factorial times 8 factorial. And I'm just going to put this in a little thought bubble. That's another equivalent way to write this expression. And I'm going to see this later in my formula as well. Okay, so we're ready for the formal definition. What we just saw in this example is what's called a K combination. So a K combination on a set of n objects, where n is greater than or equal to k, is a selection of k objects from the set of n. So I'm picking k objects from this set of n total objects, where the order in which we pick the objects does not matter. And that makes it different from a permutation, which we saw in the last videos, where the order did matter. So we can denote the number of combinations of k objects from the larger set of n. We can denote that with two different notations. We can write capital C for a combination, and then in parentheses write n comma k. That's one notation for it. The other notation for it involves writing kind of like a tall, narrow parentheses, and then up top I write an n, up on the bottom I write k. There's no fraction here. This is just another notation for this combination thing. This is typically the one that's used most often in math. It's certainly the one that I use most often. And the way I say this in words is we say n choose k. N choose k. So I personally remember that as thinking about, well, I'm choosing k objects from my set of n. And in a combination, the order does not matter. Okay. So let's see if we can express a general formula for this n choose k term. So for n choose k, in general, what we are going to have in the numerator is, I'd first think about, well, for that first object, there's n choices for what it could be. Then for the second object, there'd be n minus 1 choices. And if I keep going like this, for the kth object, there'd be n minus, in parentheses, k minus 1. Because this very first term is n minus 0. And if I'm picking k total objects, and I started at 0 here, I should end at k minus 1, not at k. All right, so, and then this whole thing, right now it's overcounting. It's overcounting as we saw with 11 times 10 times 9. So what I have to do, because I'm picking k objects, is divide by, well, how many ways are there now to rearrange those k objects? So I got to divide by, instead of 3 factorial, now it's by k factorial, because I'm picking k objects. So I get this formula in general. So I'm going to highlight this. This is my formula for n choose k in general. Okay, and of course, with this term on the numerator, I could distribute this negative sign. And if I did that, I'd get n minus k plus 1. So now what I'm going to do is I'm going to write this in another way to produce a factorial up top, like we saw in this example with our 11 choose 3. Okay, so to do that, let us go ahead. So I'm going to copy down what I have here. Let me just write it out. So I got n, we got n times n minus 1, up until n minus k plus 1, all over k factorial. And I'm going to multiply the numerator. I'm going to keep multiplying by integers, decreasing by 1 at a time. So I'll multiply it by, the next one would be just n minus k, if I subtracted this 1 away. And then it would be n minus k minus 1, up until 2 times 1. And I'll do this, whatever I do on the top, I got to do on the bottom. So n minus k times n minus k minus 1, up until 2 times 1. So now it gives me a factorial on top. I have n factorial up top. And on the bottom, I have 2 different factorials. We have this k factorial. And then this other stuff that I multiplied by, that's now n minus k factorial. So this is another way to express this formula for the number of combinations. Okay, so let's do an example where we practice using this notation a bit. So for the problem that we just did, for the number of ways to choose 3 out of the 11 books to donate, I'm going to practice this notation. This is 11 choose 3. This is 11 choose 3. So, if I practice using this factorial formula for it, I get 11 factorial up top, 11 factorial up top, divided by k factorial, which is 3 factorial, times n minus k factorial, which would be 11 minus 3 factorial. So that becomes 11 factorial over 3 factorial times 8 factorial. And as we saw above, well, that's the same thing that we are getting even up above. So that's good. This formula seems to work, at least in this one example. Okay, so follow-up question. So let's evaluate 11 choose 8. And then let's figure out, well, what does this quantity represent? So what is 11 choose 8? So, okay, let's work this out on the next page. So 11 choose 8, if I use this factorial formula, would be 11 factorial divided by, and now the k is 8 instead of 3, so I'll get 8 factorial, times 11 minus 8 factorial. So the simplifying this is 11 factorial over 8 factorial times 3 factorial. But I might notice, wait, that's the same thing as what we got for 11 choose 3. Just the two things on the bottom have switched spots. So this is the same. This is equal to 11 choose 3, which we had worked out what that value is at the beginning. That was 165. This ends up equaling 165. 165. So I'm going to box that. But, is there a reason why we'd expect these to be the same? And it turns out, yes. It turns out, so here's the way I can think about this. 11 choose 3, which we had already done. This is the number of ways to choose. We were choosing 3 out of the 11 books to donate. So 11 choose 3 is the number of ways to choose 3 out of the 11 books to donate. So in this context, what would 11 choose 8 represent? I actually want to have you pause the video and think about this for a minute on your own. Can you figure out an interpretation for what 11 choose 8 would mean that would show that it's actually the same as this? Pause it in 4, 3, 2, 1, pause it. All right, so hopefully you paused it to think about it. Let's talk about it. So what would 11 choose 8 represent? So 11 choose 8, well, this would be the number of ways to choose 8 out of 11 books to not donate. There's 8 books that I'm not going to be donating. What if I instead just counted those? This is the number of ways to choose 8 out of the 11 books to not donate. Because conceptually, those should be the same thing. If I think about how many ways there are for me to pick the books to donate, that should match the number of ways for me to pick all the books that I'm not donating. There's a one-to-one correspondence between those two things. So these should be equal. And what this illustrates, what this example with 11 choose 8 and 11 choose 3 illustrates, is the following theorem. That in general, n choose k is equal to n choose n minus k. Because of what we just saw. This I can think of as the number of ways to choose k things from the larger group of n. The other side could represent the number of ways to choose n minus k things that I don't include in the group, because that's the same. All right, and there we have it. So in the next video, we will kind of put this all together, and we'll do just a number of examples where we decide between which of these counting methods that we use to solve them.